Alrighty, we're going to try this again. Unfortunately, my previous attempt at this didn't upload. Took after 48 hours of trying to upload it, it just. So here we go. Regents Physics Unit 9, Lesson 7. We're just going to focus on compound circuit properties. This is going to be not as intense a lesson as previously done or previously done in other years. We're simply going to talk about the properties of compound circuits. We're not going to try and solve them for the Regents class. All right? Alrighty, here we go. Compound circuit. All right? Sometimes we're going to get situations where, as you can see in the diagram there, we're not going to have a pure series circuit or a pure parallel circuit. Sometimes we're going to have an intermixture of them, and that happens quite often in electronics. We often do it on purpose so that we can force a particular current to go through a particular place. Hi, Michael. And so you're going to hear me use the expression in parallel to or in series to. Okay, so what I mean by that, let's look at our diagram here. We have the voltage source, positive up here, negative down here. All right, so the conventional current is coming out and flowing this way. And as you can see, it hits this junction. Now, according to Kirchhoff's current law, that means that the current coming out here splits. So the sum of these two currents equals this one. How much goes one way and how much goes the other depends on the resistance of that particular branch. So that means that we have a parallel connection between R1 and R2 and 3. All right. The effective resistance of R2 and 3 is the two of them added up. The voltage that R1 experiences and the voltage that R2 and 3 experience are going to be the same. The voltage across R1 is not the voltage across R2. It's not the voltage across R3. The voltage across R1 is the voltage of V2 plus V3. Does that make sense? So here's our parallel connection within this circuit, okay? And so that's why you'll see the expression R1 is in parallel to R2 and 3. Now let's look at R4 over there, okay? R4 is in series to this connection right here, okay? So R4 has all the current that was flowing and split and rejoined on the far side over there, okay? So notice that the current flowing through here is the total current in the circuit. But the voltage across R4 is going to be different from and shared with this entire connection. And that's, we were dealing with that when we looked at parallel circuits, pure parallel circuits, and pure series circuits. Okay? Now, if you think about it though, this we could reduce to one resistor. All right? Take the effective resistance of those two resistances and then do the parallel circuit effective resistance equation, and we would get a single resistor value here. And notice that now, if you think of this as a single resistor plus this resistor, now you've got back to a series circuit, and we can use those properties. So let's recall the properties of series and parallel circuits. I'm going to set up a demo here and show you how this works with real light bulbs. Okay, here we go. All right, we've got our power supply over here. This is the positive terminal, this is a negative terminal, and here let's follow our path. We come out of the positive and we go into R1. All right, now R1 splits. We've got, this is the junction right here, this point, And so we got it coming in, and then some of it splits and goes through the light bulb and then comes out, and it goes around over to here to R4. You can see how this wraps around and comes back into R4. Okay, and so this is where the junction joins again. All right, so it also splits and goes through R2 and R3 and then around to R4 again. Okay, so here, this light bulb is in parallel to those two light bulbs. All right, here's how I know that. Here's how I can test it. What will happen if I turn that light bulb off? What should I see happen to these two light bulbs if they are in parallel? Think about your answer. Okay, here we go. Here's our evidence. Turn this off. Wow. All right. Now, if you remember the circuit diagram, what happens? It creates a single path for electricity to flow through. Okay. And so that's why if this one is off, now all three of these suddenly become in series. And notice that they all have to share the voltage. Since they're the same resistance, I'm using the same light bulbs here. Since they're the same resistance, that means each has to get the same voltage. Oh, remember this one was really, really bright, so it was stealing most of the voltage of the circuit. Now it's got to share it. Okay, turn this one back on. Oops. Sorry, I had some technical difficulties. So here we go again. Turn this one off. All right. Why do they all go off? I think I'm burning out a light bulb here. Okay, I have to put this on a different voltage. Now, interestingly enough, these don't appear to be on, but watch what happens when I turn this one off. Aha, they are connected. Okay, so I'm going to have to go with this connection instead. All right, notice that if I turn this one off, they're back in series like I said. Now, what if I turn one of these off? I'm going to turn it off by disconnecting it. Okay, see, these two are still connected. All right, so this is what we mean by compound circuit. All right, so we have a series connection with this light bulb, because if I turn this one off, notice that one went off too. All right, if we turn it back on, notice it, this one's on just a little bit. Okay, so this is what we mean by compound circuit. All right, now you can make complex compound circuits, you can make rather simple ones like this, and it will all help you figure out what's going on with the voltage and what's going on with the current. Or you can design it so that you know, oh, I only need half the voltage going to this one for whatever reason. Well, let me put it in parallel and put something in series with it that's going to drop the voltage. Okay, these are design things that engineering techs, electrical techs, and electrical engineers do all the time with their stuff. Okay, here we go with a little bit more of a complex circuit. All right. Instead of only 4 resistors, we've got 6 resistors. Okay. So as you can see, we've got the voltage source over there. The current would be coming out and flowing along here. Some of it splits, continues, some splits, continues. All right. Here we get another split, compound circuit. All right. Now, for our expressions here, notice that we would say R1 is in parallel to this group, R2, R3, and R4. and it's also in parallel to R5. Now, by knowing that, it should be evident that the voltage across R1 is going to be the same as the voltage across R2. It's going to be the same as the voltage across both of these resistors, but these guys have to share it. And the voltage over here is the same as R1, R2, and the sum of R3 and R4. Remember that these have the same voltage as that, and since the voltage drop across this branch, all right, these all are parallel to each other, so they all have the same voltage. It's not the source voltage, though, and that's what makes the compound circuit a little bit more problematic to deal with. This right here is throwing the wrench in the works, okay? R6 is getting its part of the share that's going over here, all right? So probably this grouping is not getting very much voltage because think about it, resistors in parallel, the effective resistance of resistors in parallel is always smaller than the smallest resistance in that parallel grouping. So this is going to result, this part of the circuit over here is going to result in a relatively small resistance. This one might be larger than that. This one might be hogging all the voltage. Okay? Going to do a different diagram and see how that changes what we're looking at. Okay, before I do that, a couple of questions. All right? One, if we were to turn off R1, take it out of the circuit, would R2, R3, R4, R5, and R6 continue operating? Think a moment for your answer. Pause the video if you need to. Okay? If R1 goes away, can I trace a path back to the source, from the source, back to the source through the other resistors? Yes. So that's how we know that R1 is a parallel connection. Notice if I just turn off R3, only R4 would go off. But if I turn off R6, the entire circuit would shut off. And that's the purpose of a switch. Consider the resistance of a switch to be very, 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 very small compared to the rest of the circuit, so that if R6 is a really, 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 really small resistance, its overall effect is low, but turn it off, and the whole thing shuts off. A switch essentially goes from low resistance, it's a wire, to ultra high resistance because now it creates a gap. It's air that's in there, so the resistance goes away. That's why switches have to be in series with what they're controlling. Okay? Okay, last circuit for this particular lesson. Voltage source, current comes out, goes through R1, splits. And now we have a parallel connection between R2, R3, and R4. Okay? Joins back together and comes back in. Current continues. The remaining current that didn't split off and go this way continues through R5 and then splits over here at that junction. Some goes through R6, R7, and R8. The rest goes through R9, joins back together, joins back with what went through here. Total current returns to the voltage source. Questions for you. Okay? Is the voltage across R1 equal to the voltage across R2? Okay, think about that. I'm going to save this one for when we have our online meeting. Is the voltage across R2 the same as the voltage that's across this branch over here? In other words, is V3 plus V4 equal to V2? is this taking away some of the voltage from this over here? Is V9 equal to V6 plus V7 plus V8? Is the voltage of this segment over here equal to the voltage of this segment over here? Okay? So I'm going to hold on to this. I'll keep it ready for our online meeting for this particular lesson. Please check your emails for it. All right? Have a good one, and I will see you when we have our online meeting. Okay, this concludes the lesson for compound circuits. Um, uh, Hopefully, everything uploads with this one, and you'll be able to see it. If not, we're going to have some. I'm going to be very angry with technology. So this is your friendly heavy physics teacher signing off one more time. Hopefully we'll get through this COVID-19 stuff, and I'll see you back at school shortly. I don't know how shortly is going to be, though. Have a good one.